Have you ever wondered what happens when the two most important metals in our modern infrastructure just flat out refuse to get along? I mean, copper and aluminum are the absolute workhorses of our electrical and mechanical systems. But here's the crazy part. When you force them to interact directly, it can literally cause our infrastructure to self-destruct. So, welcome to this explainer. We're going to unpack this fascinating and honestly highly destructive metallic rivalry.
Okay, let's just quickly look at our agenda for today. We're going to start with the tale of two metals, then we'll look at mining the ampacity gap, followed by the galvanic corrosion threat, corrosive environments as accelerants, and finally, engineering the solution.
All right, jumping right into sections 1 and 2, the tale of two metals, and minding the ampacity gap. To really wrap our heads around these two metals, we have to look at the very clear performance gap between them. So check out this data from SorrelWire. It shows the safe continuous current, which we call ampacity, for different wire gauges at 75 degrees Celsius. Notice how a standard 12-gauge copper wire, the exact kind sitting inside your home's walls right now, can safely carry 25 amps. But if you look at the exact same size in aluminum, it can only handle 20 amps. And it's the same story at 10-gauge. Copper handles 35 amps compared to aluminum's 30. So across the board, copper just consistently carries a higher load safely.
And understanding that ampacity is absolutely vital for safety, right? Because the number of electrical devices on a circuit determines your overall load. So to figure out exactly what wire size you need so you don't accidentally overheat the whole system, you simply add up the wattage of all your connected devices and divide it by your standard system voltage. Usually that's 120 or 240. That simple bit of math gives you your required amps, which tells you for sure whether you need the higher capacity of copper or if aluminum is going to do the trick.
But what actually happens when these metals physically touch to transfer all that power or heat? That brings us to section 3, the galvanic corrosion threat.
Honestly, the best way to think about galvanic corrosion is like a highly toxic relationship. When you take two totally dissimilar metals, like copper and aluminum, and you force them into direct contact, and then you introduce a third wheel, like water or salt, well, they begin to literally destroy each other. It's an electrochemical reaction that actively eats away at the materials. There's just no way around it.
To see how this plays out in the real world, let's look at your typical HVAC system. So what we have here is a standard round tube plate fin or RTPF coil before any corrosion has happened. Manufacturers get this fantastic thermal efficiency by mechanically bonding copper tubes directly to those wavy aluminum fins. Now for heat transfer that's great, but as we just learned, it creates the absolute perfect bimetallic setup for a galvanic reaction the second an electrolyte enters the chat. And this brilliantly, or maybe tragically, illustrates the aftermath. Just look at the interface right where the copper and aluminum meet. The aluminum fin basically acts as a sacrificial anode and actually corrodes right at the contact point. And not only does this physical destruction completely ruin the thermal conductivity between the tube and the fin, but it also creates these nasty aluminum oxide deposits that build up and block the airflow completely. The system literally suffocates itself.
So you might be wondering, where do these electrolytes even come from? Let's move to section 4, accelerants and corrosive environments.
Let's look at the two major macro-environmental culprits. Out in coastal and marine environments, sea spray and fog carry sodium chloride, salt, miles inland, depositing a highly conductive electrolyte right onto your metal coils. Meanwhile, on the flip side, heavy industrial environments pump out sulfur oxides and nitrogen oxides from combustion. These mix with moisture in the air to create acidic dew or even acid rain. Both of these massive macro environments act as extreme accelerants for system failure. But maybe you live inland, far away from the coast or heavy industry. You're totally safe, right? Well, actually, scratch that. You really have to watch out for localized microenvironments. If your equipment is placed within just 50 feet of a laundry vent, pumping out cleaning chemicals, heavy diesel traffic, a sewer vent, or even heavy fertilizer use, you've accidentally created a highly corrosive localized zone. Just think about that for a second. A simple laundry vent right next to your house can destroy an unprotected system just as fast as a salty coastal breeze. Thankfully, we aren't completely helpless against all this chemistry. Which brings us to section 5, engineering the solution. Over in the electrical world, the go-to solution is the bimetallic lug. This is a clever connector featuring an aluminum barrel and a copper palm, and they are friction welded together. It physically isolates the two wire types to stop a galvanic cell from forming, all while allowing seamless power transfer. But to install it properly, an electrician has to first perfectly clean and strip the aluminum, insert both metals into their respective sides, crimp it incredibly firmly for mechanical strength and conductivity, and finally apply an anti-oxidation compound to completely seal out the environment. It's a whole process, but it works.
Now let's pivot to the HVAC side and see how this works in complex mechanical systems. Manufacturers like Carrier utilize microchannel heat exchangers or MCHX coils. Notice the flat tube design here. These are made entirely of carefully chosen aluminum alloys, but the real genius, that's in the coating. They use zinc-enriched surfaces. It's kind of similar to galvanized steel. This zinc layer intentionally weathers laterally, meaning it spreads harmlessly sideways across the surface, rather than allowing corrosion pits to dig deeply into the tube and cause a catastrophic refrigerant leak.
For even more protection, we can step up to advanced barrier coatings. If you're in a mildly corrosive coastal area, you can use pre-coated fins. This is a baked-on, non-metallic layer applied before the fin is even stamped, and it literally acts as an electrical insulator between the copper and aluminum. But what about severe industrial environments? For that, you need Carrier's e-coating process. This electro-coating process bonds a flexible, highly durable, and totally impermeable epoxy across the entire coil, completely encapsulating it and sealing the electrolyte out entirely. The whole shebang is protected. So as we wrap up this explainer, I want to leave you with this really powerful quote from our sources. Copper is a strategic national resource. It's highly efficient, incredibly valuable, and utterly foundational to the grid that powers our lives. Knowing how it interacts with its partner, aluminum, and understanding the sheer environmental threats they both face leaves us with a vital question to ponder. As we build the next generation of our world's infrastructure, how will you ensure we are properly engineering, connecting, and protecting these absolutely indispensable materials?